the Axler book is a little bit unusual in that it doesn't define determinant and trace and other invariants of linear transformations until the very end. I'm going to define them now because it'll be useful to connect them to other places that you might have seen in the past. And we'll now be talking about situations where they occur. So though they won't be in the critical path really until the end, I want to give the definitions. So let's let f be a linear operator and b be a basis. A basis which makes the matrix with respect to b, remember that's the same as saying the matrix using the basis b on both the rows and the columns, upper triangular. And now here's the definition. Trace of f is the sum of the diagonal entries. Of this matrix, this upper triangular matrix. And the determinant of f is the product of the diagonal entries. Of M, B, and F. So as I've defined them here, it's not yet obvious that they don't depend on the choice of basis, but in fact they don't. And towards the end today, I'll talk about reasons why that's true. We'll eventually prove that. And you could think about there being other kind of intermediate concepts. Right? So both of these are polynomials in the entries of this matrix, and they're both symmetric in the sense that if I changed what was on the diagonal, like if I had a diagonal matrix and I permuted the entries, neither of these would be different. Neither of these would change. And you could think about there being other invariant polynomials that are between trace and determinant, maybe sums of all, sums of products where the products are less than all of them. Right? So sums of products of 5 or something like that, and we'll talk about those a little bit later too. Okay. We'll just use these definitions as an aside for now as we continue. Okay, so let's look at some of the properties of upper triangular matrices. Suppose f is a linear transformation, and it's upper triangular. It has an upper triangular matrix with respect to some basis b. Then f is invertible, and remember that for a linear operator, f invertible is the same as injective, is the same as surjective, is the same as isomorphism. If and only if all diagonal entries of the matrix of f are non-zero. Yeah.
Triangular matrix.
Upper triangular.
No, I mean, it has an upper triangular matrix.
With respect to WRT, with respect to the basis B. And because a list of numbers is non-zero, a list of field elements is non-zero if and only if their product is non-zero, and their product is this determinant, I can say if and only if the determinant of f is non-zero. Okay, so you may have, if you've taken another class on matrices, you may have had this We've seen determinant of f being non-zero is the same as it being invertible. The purpose of doing this right now is to connect it back to that. Okay. So let's give a proof of that. So let's let B be a basis, n vectors, that makes F upper triangular. That is, the matrix with respect to B of F has the form lambda 1, lambda 2, lambda n on the diagonal, 0 below the diagonal, and some stuff we're not that interested in above the diagonal. On the one hand, suppose we have some lambda I, which is equal to 0. We want to show that F is not invertible. Well, if it's lambda 1, that's easy. That means that F of V1 is equal to the 0 vector. And V1 is a basis element, so in particular it's not 0. So F has a kernel, F has a null space, F is not injective, and F is not invertible. If for some k greater than 1, lambda k is equal to 0, one of these lambda k's is equal to 0, then that means that F sends each V1 up to Vk, and therefore the span of those V1 up to Vk, V1 up to Vk, everything in the span of those vectors up to the kth place, to something in the span of V1 up to Vk minus 1. So it's sending a k-dimensional space to a k minus 1 dimensional space, a lower dimensional space. So F restricted to, say, the span of V1 up to Vk is not injective, which you can prove, for example, by thinking about the rank nullity. So that means there's some u in this span with f of u equal to 0. And that u is also in V. Okay, so F has non-trivial null space, and F is not invertible. On the other hand, suppose F is not invertible. Well, that means that it's not injective. That means that its null space is not the 0 vector. That means there exists a V in V, which F sends to 0. Since V1 up to Vn were a basis for F, I can write this vector V as a linear combination of the basis elements, and I'm going to leave off all the basis elements above the last coefficient, which is non-zero. Then V is equal to, then that means 0 equals F of V equals F of this linear combination and since F is linear, I can push it through. A1 F of V1, AK F of VK. I could take this AKF of VK and move it to the other side by subtracting it. So then what I've done is, and this is non-zero, so I've expressed f of vk, whatever it is, as an element in the span of the vectors that come before it, v1 up to vk minus 1. And what does that mean in terms of the matrix? It means that f of vk is expressible in terms of coefficients for basis vectors v1 up to vk minus 1. And the vk vector I could take to be 0. So that means, therefore, this lambda k is equal to 0. So the definition that I'm erasing now will become a little bit more interesting with this next proposition, which I've said, I think, already, but let's prove it. Suppose that B is a basis, V, making F in LV upper triangular. Then the eigenvalues of F are the entries on the diagonal of the matrix with respect to the basis B of F. That means that the trace is the sum of these eigenvalues, counted sometimes repeatedly, and the determinant is the product of the eigenvalues, counted repeatedly. Some of them happen more than once. Proof. Okay. Consider a number lambda in the field. And we'd like to test whether it's an eigenvalue. To test whether it's an eigenvalue, we have multiple equivalent conditions. Lambda, one of them is that lambda is an eigenvalue of F if and only if F minus lambda times the identity is not invertible, has a non-trivial null space. And the null space of that is the eigenspace associated with lambda. I'd like that to be not the zero vector space. And well, this is not invertible if and only if its matrix is not invertible. And either of those, connecting with the previous proposition, let's take the matrix of F minus lambda times the identity of V. What does that matrix look like? Well, it starts out looking like this, MB of F. Lambda 1, zeros below the diagonal, lambda 1, lambda 2, up to lambda n. And then we've subtracted lambda times the identity. In any basis, the identity transformation has matrix all ones on the diagonal and zeros everywhere else. And so this is just lambda 1 minus lambda, lambda 2 minus lambda, and so on, lambda n minus lambda. Okay, so that's the matrix. And there's some stuff we don't care about up there, which isn't changed. So that's the matrix. And we know from the previous proposition that this is not invertible if and only if one of these things is 0. But to say one of these is 0 is the same as saying that lambda is equal to one of them. Right? invertible if and only if lambda equals lambda j for some j. Okay, so that means that we take those definitions, the first definitions we saw of trace and determinant, we can rewrite those as trace of f is the sum of eigenvalues counted with multiplicity. And we haven't said exactly what we mean by that, but that means that some of them can occur more than once, right? I mean, the trace of the identity matrix has to be the sum 1 plus 1 plus 1 plus 1, in this case, or 4. And so somehow this eigenvalue 1 is being counted more than once. And the determinant of f is the product of eigenvalues. Again, counted with multiplicity. Okay, so even better, of course, than an upper triangular matrix is a diagonal matrix. When we started talking about nice forms for matrices, that was our first example. And now that we know a little bit more about eigenvalues, let's zoom in on that example, on that situation. Diagonal matrix is one which has something on the diagonal which could be 0 and zeros everywhere else. So it's both upper triangular and lower triangular. Its trace is the sum of these things. Its determinant is the product of those things. And of course, a linear operator has a diagonal matrix. With respect to the basis, just say in the basis, v1 up to vn, if f of v1 is some scalar times v1, f of v2 is some scalar times v2, and so on. But that's the same as saying that these are the eigenvalues of it, right? They're non-zero vectors such that f of that vector is equal to lambda times this vector. So i.e., if and only if v, the vector space v that f acts on, has a basis consisting entirely of eigenvectors of f. So that's what it means to be diagonal. You have a basis consisting of eigenvalues. Though the word basis appears, I mean, that I can say that about f without telling you any particular basis. Right? So I could say a diagonal f. That is not a crazy thing to say, even without specifying the basis. It means there exists a basis, the eigenvectors. Okay, so watch out, not every f, not every operator has such a thing. Has a diagonalizing basis, even over C. So we'll be very concerned in the next few weeks with figuring out exactly which matrices, which operators do have diagonal matrices in some basis. And that's what leads us to these spectral theorems, which are some of the most important theorems in the class. So it doesn't always have one. So let's give an example. The linear operator, which goes, say, C2 to C2, that is lists of two field elements with the usual addition and multiplication, scalar multiplication. F of WZ is equal to Z0. this thing has matrix. In this basis, it has the matrix 0, 0, 0, 1. I've just shifted. You can see that its trace and its determinant are both going to be 0. It's upper triangular. It only has 0 as an eigenvalue, so if I were to have any hope of finding a basis for it that consisted of eigenvectors, I would need to find a two-dimensional eigenspace and pick 2 eigenvectors in that. So the first question is eigenspace of its only eigenvalue, which is 0. Is the eigenspace associated to 0 for the matrix F, for the linear transformation F. Of course, that's the null space of F minus lambda times the identity. And in this case, this is just vectors of the form W0 with W in a complex number. So this null space is just one-dimensional, and I would need a two-dimensional to get something which is spanned by the eigenbasis. And if you have seen such things before, you can see this matrix is already in what's called Jordan normal form that we'll learn about later. And if you know about that, you know already that you can't do any better than this. There's no triangular basis for it, and no diagonal basis for it. Okay, so I said that these spectral theorems that we'll get to will tell us exactly when a diagonalizing basis exists. But here's a sufficient condition that connects with something we've already done, which is that if I have a map, a linear operator f and L of v, and it has dim v distinct eigenvalues, so it's n-dimensional, has n distinct eigenvalues, then F does have a diagonal matrix. It has a large enough eigenspace for all of its eigenvalues with respect to some basis. V. So this is enough to have a diagonal matrix, but not every diagonalizable operator has this property. Proof, suppose F has dim v distinct eigenvalues. Lambda 1 up to lambda n, which is equal to dim v. So let v1 up to vn be corresponding eigenvectors, corresponding non-zero eigenvectors. So we had a theorem earlier that said that in such a case, these vectors v1 up to vn are linearly independent. So we have a linearly independent list. Its length is the dimension of the vector space. So they are a basis. And a basis of eigenvectors. So whenever I apply f to vi, I get out lambda I vi. And so in that basis, the basis of associated eigenvectors, non-zero eigenvectors, f will have a diagonal matrix.